Chapter 1, Page 1. The Beginner's Guide to Understanding the Prime Numbers Hexfiltration Method. Techniques for Deriving the Pattern of Prime Numbers by Seth Snare. Also narrated by Seth Snare. Chapter 1, Splitting Hairs. Almost anyone who is familiar with computers knows that these devices think in what is called the binary number system, in which all points of data are represented as either a 0 or 1. Many of those people also know that computers have another number system called the hexadecimal system, which correlates directly to a computer's binary number usage. For example, the base hex numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And each of these digits correlate directly to the binary number system in a pattern as 0000, 0001, 0010, 0011, 0100, 0100, 0101, 0110, 0111, 1000, 1001, 1010, 1011, 1100, 1101, 1110, 1111. This should be considered basic knowledge for an advanced computer student and techie. This knowledge is imperative for anyone who desires to learn the hexfiltration method. With this method, the hex digits are used to build the prime numbers pattern, which can be mapped to either a fleshed out chart, which is easier for human use, or a single string of hexadecimal digits, easiest for computers. From this point on, unless otherwise specifically stated, this text will reference the mapped chart method, as this book is, after all, intended to instruct humans, not computers. Now please look at example chart number 1A. As you can see with the example chart, there's a seemingly crazy array of numbers and letters thrown about. I hope to put your troubled mind at ease. If you look closely at the chart, you should notice a set of base 10 numbers at the extreme left and top of the page. These numbers, as I expect you've already guessed, establish the rows and columns for the hex digit patterns to be placed in an organized grid. If you carefully trace each row from left to right along the chart, you can then work out that a pattern is revealed within each row. Now, if you trace each column, things seem to lose cohesion. This, I assure you, is not the case. The reason the digits laid out in each column seem random is understandable. Let me explain a few important details. Earlier I mentioned that to understand the hexfiltration method, you must understand the correlation between the hexadecimal number system and the binary number system. Well, here's the point where that knowledge comes in handy. See, each hex digit in a given column represents part of the pattern for determining the prime or non-prime value of a specific set of 4 base 10 numbers, which happen to be the ones we actually want to know about. Remember that every hex digit directly correlates to 4 binary digits, and it's these digits that are associated with each base 10 number. Maybe this sounds strange, but it works. The whole point of this method is to determine which numbers are prime and which ones aren't. If you don't think that sounds very intuitive, well, I understand. As a reminder from those grade school days, prime numbers are defined as those curious and unique numbers that can only be divided evenly by 1 and themselves. Give it a chance, and you should see that it's more simplistic than it seems at first glance. Do you remember how I mentioned that each of the hex digits correspond to a group of exactly 4 binary digits? It's this correlation that allows each column set on the Hexfiltration chart to represent the 4 base 10 digits that I made mention of previously. And yes, I know I'm repeating myself, but that's only because of how important it is to understand this point. Once you fully grasp this concept, you can begin to use an algebraic formula that reveals what the numbers actually are. For example, look up column number 5 on the example Hexfiltration chart. As you can see for yourself, this column contains several hex digits, but shows no base 10 digits, except for the column heading digit itself. As I've explained, each column represents 4 actual numbers, so an inquiring mind might ask, what are these 4 numbers, and how can I tell if they are prime? Well, as it turns out, the solution is simple. Use the column heading number, which of course in this example happens to be the number 5. You multiply it by 8 and then simply add 1 to it. For the purpose of this example, you should be able to easily calculate that the result of this little equation is the number 41. This is the first number out of 4 in the sequence of odd numbers that the column is designed to represent. But there are still 3 more to figure out. Fortunately, that's easy. You know how to count by 2, right? Of course you do. Just start from the one we found and increase by 2. For example, 41 plus 2 equals 43. 43 plus 2 equals 45. 45 plus 2 equals 47. There you go. Now you have all 4 of the numbers that correlate with this column, i.e. 41, 43, 45, 47. Why is this? Well, think about it like this. Starting at column number 0, the number sequence being represented goes 1, 3, 5, 7. Then column number 1 goes 9, 11, 13, 15. Do you see what's going on yet? The number system is counting the odd values upward into infinity. Each column simply organizes these odd numbers into groups of 4 so that the hex/binary digits can correspond to them. As a bonus to doing this, each number in the group can be calculated directly with that equation I just showed you. Go ahead, try it a few more times with some of the other columns. Well, I hope you tested it out as I suggested. Now that we've got a good grasp on that topic, I'd like to show you a little trick for specifically calculating those final 3 numbers represented in the column set I talked about. I know that adding 2 to each number is pretty easy, but as it so happens, there's a more direct method you can use. In the last example, we learned how to calculate the first base 10 number in the group set by using the heading number and a simple equation. Well, that same equation still applies for calculating the final 3 numbers in the group represented by each column. I'd like us to work this out for each number in the sequence, but to do this, we have to work backwards to illustrate my point. It's not difficult, so please stay with me here. Let's start with the first number, which we all know to be 41 from the previous example. Subtract 1, then divide the result by 8. Well, what'd you get? The result is 5, of course. But when you try it with any of the other 3 numbers, you get a slightly different result. Go ahead, try it now. As you can see, number 43 returns 5.25, number 45 returns 5.5, and number 47 returns 5.75. If you haven't figured it out yet, the first number being represented by each column will always calculate to the column heading number directly, and the following 3 will calculate directly to the column heading number plus a fraction of 4, in the order of 1/4, 2/4, 3/4. I like to think the first number is being calculated with the column heading plus the fraction 0/4. With this knowledge, You can always determine any number in any column being represented. Let's attempt a different example. How about the third number in column 25? Okay, well, you know from what I showed you that the third number is always calculated using the column heading plus 2/4, which in this case is 25.5. So using the formula 25.5 times 8, then you add 1, you should arrive at 205. That is, of course, if you calculated everything correctly, and I've no doubt that you have. What do you say you go ahead and try a few more? How about the fourth number in column 7? Or how about column 34? These are good ones to try on your own. Go ahead. I'm sure you've got this down. Okay. I think it best to go ahead and end this chapter right here. But I suspect you might be wondering how all this determines whether a number is prime or not. Well, if you're wondering such things, I have to say, that's a very legitimate point, but I hope you're not getting impatient with me. Understanding all this takes a few baby steps at first, but I assure you, you will get there.